When dealing with parallel feeders such as the 500 mcm aluminum conductors described, correctly sizing equipment bonding jumpers within individual conduits is critical. These jumpers play a vital role in equalizing potential differences among metallic raceways and equipment enclosures, ensuring a safe and effective path for fault current. The governing standard for this is Table 250.122 of the National Electrical Code, often referred to as the NEC. NEC Section 250.122 specifically addresses the sizing of equipment bonding jumpers. It provides minimum size requirements based on the size of the ungrounded conductors, also known as phase conductors. The key principle is that the equipment bonding jumper must be appropriately sized to handle the potential fault current it might be required to carry. The NEC uses the size of the ungrounded conductors as a proxy for the anticipated fault current. Since you have parallel feeders, the equipment bonding jumper size is determined by the combined size of the parallel conductors. In the case of 500 mcm aluminum conductors, Table 250.122 dictates the minimum equipment bonding jumper size. Consulting the table for 500 mcm aluminum, the corresponding minimum size for the equipment bonding jumper is 2 AWG copper or 4 AWG aluminum. This requirement stems from the fact that parallel conductors, by their very nature, increase the potential fault current compared to a single conductor of equivalent ampacity. Therefore, the equipment bonding jumper needs to be larger to safely handle this increased current. Now let's delve a bit deeper into the reasoning behind this requirement. Equipment bonding jumpers are not intended to carry continuous load current. Their primary purpose is to provide a low impedance path for fault current to return to the source in the event of a ground fault. This low impedance path is essential for quickly tripping the overcurrent protective device, such as a circuit breaker or fuse, thereby minimizing the risk of electrical shock or fire. If the equipment bonding jumper is undersized, it may not be able to handle the fault current effectively. This could result in a slower tripping time for the overcurrent protective device, increasing the potential for damage and hazards. Furthermore, an undersized jumper could overheat and potentially melt, creating an open circuit in the grounding path, which is a dangerous situation. It's also important to note that the equipment bonding jumper must be properly connected to both the metallic raceway and the equipment enclosure. This connection should be made using approved connectors and methods to ensure a reliable and low impedance connection. The NEC provides specific requirements for these connections in Article 250. In addition to sizing the equipment bonding jumper based on Table 250.122, it is always prudent to consider other factors that may influence the required size. For example, if the installation is subject to high fault current conditions, it may be necessary to increase the size of the jumper beyond the minimum required by the table. This decision should be based on a thorough engineering analysis of the specific installation. The NEC provides guidance on how to perform such an analysis in Article 250. Remember that the information provided here is for general guidance only and should not be considered a substitute for professional engineering advice. It is always best to consult with a qualified electrical engineer or inspector to ensure that your installation complies with all applicable codes and standards. Let's examine some additional considerations for equipment bonding jumpers. Firstly, the length of the equipment bonding jumper is important. While there is no specific length limitation, the general principle is to keep it as short as possible. A longer jumper introduces more impedance into the grounding path, which can reduce its effectiveness. Secondly, the material of the equipment bonding jumper is also crucial. Copper is generally preferred due to its lower impedance compared to aluminum for the same gauge size. However, aluminum can be used if it is properly sized and installed, paying attention to termination methods to avoid corrosion. Thirdly, consider the type of raceway. If you are using metallic conduit, the conduit itself serves as part of the equipment grounding path. However, an equipment bonding jumper is still required to connect the conduit to the equipment enclosure. If you are using non-metallic conduit, a separate equipment grounding conductor must be run inside the conduit and connected to the equipment enclosure. Fourthly, inspect the equipment bonding jumper periodically. Over time, connections can loosen or corrode, which can increase the impedance of the grounding path. Regular inspection and maintenance can help ensure that the grounding system remains effective. Fifthly, do not confuse equipment bonding jumpers with equipment grounding conductors. While both serve to provide a path for fault current, they have different functions. Equipment bonding jumpers connect metallic parts of the electrical system together, while equipment grounding conductors connect the equipment to the grounding electrode system. Sixthly, always consult the latest edition of the NEC. The electrical codes and standards are constantly evolving to keep pace with technological advancements and new safety concerns. Make sure you are using the most up-to-date information when designing and installing electrical systems. Seventhly, consider the environment. If the installation is in a corrosive environment, such as a coastal area or an industrial plant, you may need to use special materials or methods to protect the equipment bonding jumper from corrosion. Eighthly, documentation is essential. Keep accurate records of the size and type of equipment bonding jumpers used in the installation. This information can be helpful for future maintenance and troubleshooting. Ninthly, training is vital. Ensure that all personnel involved in the installation and maintenance of electrical systems are properly trained in the NEC and other applicable standards. Tenthly, when in doubt, seek expert advice. If you are unsure about any aspect of the installation, it is always best to consult with a qualified electrical engineer or inspector. They can provide guidance and help ensure that the installation is safe and compliant with all applicable codes and standards. Now let's address some common mistakes when sizing equipment bonding jumpers. A common mistake is to simply assume that a small jumper is sufficient, without properly consulting Table 250.122. This can lead to an undersized jumper that cannot effectively handle fault current. Another mistake is to use the wrong table. Table 250.122 is specifically for equipment bonding jumpers. Other tables, such as Table 250.66, apply to different types of grounding conductors. Another common mistake is to neglect the combined size of parallel conductors. When dealing with parallel feeders, it is essential to consider the total ampacity of all conductors when determining the required size of the equipment bonding jumper. Another mistake is to use improper termination methods. A loose or corroded connection can significantly increase the impedance of the grounding path, rendering it ineffective. Use approved connectors and methods to ensure a reliable connection. Another mistake is to overlook the environment. Corrosive environments can degrade the equipment bonding jumper over time, reducing its effectiveness. Use appropriate materials and methods to protect the jumper from corrosion. Another mistake is to fail to inspect and maintain the equipment bonding jumper regularly. Over time, connections can loosen or corrode, which can compromise the grounding system. Regular inspection and maintenance are essential. Another mistake is to neglect documentation. Accurate records of the equipment bonding jumper size and type can be helpful for future maintenance and troubleshooting. Another mistake is to assume that the conduit is sufficient. While metallic conduit can serve as part of the grounding path, an equipment bonding jumper is still required to connect the conduit to the equipment enclosure. Another mistake is to not seek expert advice when needed. If you are unsure about any aspect of the installation, it is always best to consult with a qualified electrical engineer or inspector. Furthermore, let's delve into specific scenarios and applications to better illustrate the correct sizing of equipment bonding jumpers for parallel feeders. Firstly, consider a scenario where you have two sets of parallel 500 mcm aluminum conductors feeding a distribution panel. According to Table 250.122, a single 500 mcm aluminum conductor requires a minimum 4 AWG aluminum equipment bonding jumper. Since you have two sets of 500 mcm aluminum conductors, you might initially think you need to double the size of the jumper. However, the NEC only requires you to size the jumper based on the combined size of the conductors, not to provide a separate jumper for each conductor. Therefore, you would still use a 4 AWG aluminum jumper for each conduit containing the 500 mcm aluminum conductors. Secondly, imagine you are using a different material for the equipment bonding jumper, such as copper. In this case, you would need to consult Table 250.122 to determine the equivalent copper size for a 500 mcm aluminum conductor. As mentioned earlier, the table specifies a 2 AWG copper jumper as equivalent to a 4 AWG aluminum jumper for a 500 mcm aluminum conductor. Thirdly, consider a scenario where you have multiple conduits containing parallel feeders. In this case, you would need to install an equipment bonding jumper in each conduit to ensure that all metallic raceways are properly bonded together. The size of each jumper would be determined by the size of the conductors in that particular conduit. Fourthly, imagine you are dealing with a high fault current environment, such as an industrial plant with large motors. In this case, you may need to increase the size of the equipment bonding jumper beyond the minimum required by Table 250.122. This decision should be based on a thorough engineering analysis of the specific installation. Fifthly, if you are using flexible metal conduit or liquid-tight flexible metal conduit, the NEC has specific requirements for the equipment grounding conductor. In some cases, the conduit itself may not be sufficient for grounding, and a separate equipment grounding conductor may be required. Sixthly, if you are using a grounding busbar in the equipment enclosure, ensure that the equipment bonding jumpers are properly connected to the busbar using approved connectors. The busbar should be sized to handle the total fault current that may be imposed upon it. Seventhly, always refer to the manufacturer's instructions for the equipment being installed. The manufacturer may have specific requirements for grounding and bonding that must be followed. Eighthly, consider the impact of voltage drop on the grounding system. A long equipment bonding jumper can contribute to voltage drop, which can reduce the effectiveness of the grounding system. Keep the jumper as short as possible to minimize voltage drop. Ninthly, when installing equipment bonding jumpers in wet locations, use waterproof connectors and materials to prevent corrosion. Tenthly, when working with aluminum conductors, use oxide-inhibiting compounds to prevent corrosion at the connections. 11thly, document the location and size of all equipment bonding jumpers in the electrical system drawings. This information can be helpful for future maintenance and troubleshooting. 12thly, provide training to all personnel who will be working on the electrical system to ensure that they understand the importance of proper grounding and bonding. 13thly, conduct regular inspections of the electrical system to identify any potential grounding and bonding problems. 14thly, develop a written grounding and bonding plan for the facility to ensure that all grounding and bonding requirements are met. 15thly, consult with a qualified electrical engineer or inspector to review the grounding and bonding plan and to ensure that it complies with all applicable codes and standards. 16thly, ensure that all equipment grounding conductors are properly identified with green tape or other approved markings. 17thly, use a ground resistance tester to verify the effectiveness of the grounding system. 18thly, consider the use of surge protective devices to protect sensitive electronic equipment from damage due to voltage surges. 19thly, install ground fault circuit interrupters in areas where there is a high risk of electrical shock, such as bathrooms and kitchens. 20thly, use only approved equipment and materials for grounding and bonding. 21stly, ensure that all electrical panels and enclosures are properly grounded. 22ndly, when working on electrical systems, always de-energize the circuit and lock out and tag out the disconnect switch to prevent accidental energization. 23rdly, use a voltmeter to verify that the circuit is de-energized before working on it. 24thly, wear appropriate personal protective equipment, such as rubber gloves and safety glasses, when working on electrical systems. 25thly, never work on electrical systems alone. Always have another person present in case of an emergency. 26thly, if you are not qualified to work on electrical systems, do not attempt to do so. Contact a qualified electrician. 27thly, always follow the manufacturer's instructions when installing and maintaining electrical equipment. 28thly, keep all electrical equipment clean and free of debris. 29thly, inspect electrical cords and plugs regularly for damage. 30thly, do not overload electrical circuits. 31stly, use extension cords only temporarily. 32ndly, do not run extension cords under rugs or furniture. 33rdly, keep flammable materials away from electrical equipment. 34thly, have a fire extinguisher readily available in case of an electrical fire. 35thly, know the location of the main electrical disconnect switch. 36thly, teach children about electrical safety. 37thly, if you experience an electrical shock, seek medical attention immediately. 38thly, if you see a down power line, stay away from it and call the power company. 39thly, if you smell gas, evacuate the building and call the gas company. 40thly, if you have any questions about electrical safety, contact a qualified electrician or your local electrical inspector.